I'm going to talk about some fundamentals of the coordinate system and position vectors and some basic operations. So light wave is a y-up, left-handed coordinate system. That means that the y-axis is the one pointing up, and a positive rotation can be basically described by putting the left hand thumb up and closing fingers. That describes a positive rotation in light wave. So it's called left-handed or clockwise, as we can see here. So this is the positive direction of a rotate here. Now, this is something only to consider when, for example, you're seeing materials done for other coordinate systems and you want to implement some of those solutions either from them in Lightwave, or you want to apply something that you've done in Lightwave in other places. So something to consider. We have the basics of the 3D space, which is the world space or the scene space. It's the space that is a fixed reference. So other spaces, we might define other spaces, like when I move this object here around, I'm moving it away from the origin. So I could say I'm defining a space with this object, but the world space is a fixed reference. So we have the origin, which is 0, 0, 0, and we have the standard basis unit vector. So these are concepts, not actually things that you can set up on, let's say, Lightwave options, but these are the three vectors that define the coordinate system. So we have I hat, j hat, and k hat that define the x-axis, the y-axis, and the z-axis. So they define the length of one unit. They define the direction, the orientation of the axis, and they also define what the positive and the negative side are. So if I turn it on here, you can see that. And in other situations, we're kind of going to change those, and it's like changing the coordinate system. And so basically these can be very customizable. So here I'm changing the origin, so I'm moving this position away from the origin, just like I move this one here, and so on. But for this particular case, for the world space, we are talking about something that is a fixed reference. All other spaces relate to the scene space. So we need a fixed reference so that everything has something in common to relate to, and this is it. Now let's look into some position vector notation. So a vector is a geometric construct that has a direction and that has a length or magnitude and the direction. And here we deal with them we don't deal with them on those quantities. We don't define them and we don't manipulate them mostly on those characteristics. We do them by their points, or by actually just one point. So a vector can be defined by a length in the direction, but also by 2 points, the tail point and the head point. Now we're dealing with position vectors, which are vectors that the tail point is bound to the origin. So the tail point is always defined for us. We never manipulate it in a way. It's always at the origin, 0, 0, 0. This means that we are left to basically manipulate a single point to define a vector. If I have this becomes a bit more obvious. For example, let's say I have two points, let's say point A and point B, and I say, well, find the angle between these 2 points. And so it sounds like a strange question, like there are points, how do they make an angle? So we have, of course, to introduce the origin and connect to those positions. And now obviously there's an angle between them. So the origin is always implicit, but many times we go back and forth between a vector or a position, because in a way, since we can't define vectors with a single position, it's common to sometimes treat them that's why we have x, y, z, and we call it a vector. So get used to it. So this would be the vector OA, the vector that has the tail point at the origin and the head point at A. But many times you just consider the position A as the vector. So sometimes there's that interchangeability. Now there's things that can be inferred from a position vector that relate to what I said here. So there's a length, and we can check that length with the length node. So basically the length is just length, norm, or magnitude. Basically it's the distance from the head point to the origin. So this is something that we can check for. Another thing we can check for is the direction, and a vector that is in a format that is very useful for to define a direction. And so that's a unit vector, which is basically a copy of this vector, but with length 1. So these vectors are written with a little hat, just like here, I hat, j hat, and k hat. They are written with a little hat in it. So this means that it's a unit vector, a vector with length 1. So to calculate the length, of course, here we have the Pythagorean theorem, but we don't need to go into those calculations. Just apply the length node, and to find the unit vector, we could basically divide the coordinates. In this case, I have 2, 3, 4. And so if I would divide the length of the vector to its coordinates, I would get the unit vector. So basically, I have something with length 5. If I divide the vector, the coordinates of the head point by 5, I'm going to get something that has length 1. So, but we're not going to do that. So it can just use this node called normalize that will output any vector into a unit vector. Of course, there's an exception, and that exception is 0, 0. So 0 length vectors cannot be normalized, and their length is going to be 0. So let's look into some basic operation. Oh yeah, I think I have this here to show as well. The scale node. So the scale node is like I've said here. So it's basically a scalar, a vector being multiplied by a scalar. So let's say if I have the vector 2, 4, 0, if I multiply it by a scalar of 1, I'm going to get the vector as it is. If I multiply it by 2, I'm going to have a similar vector, but it's going to have double the length. So here I'm going to have 2 times the length. And if I multiply by a negative number, so here I'm going to have, let's say, minus 0.5, I'm going to have 0.5 the length, but I'm also going to flip the direction. So now the vector, since it was scaled by a negative value, the direction was flipped. So not the same direction, the inverse direction. Now let's look into add. So this is a very fundamental operation. We have vector A and we have vector B. And if I add B to A to explain this in a geometric way, so here we have the algebraic explanation. Basically, by each component, we add the pair in the 2 vectors. So AX plus BX, AY plus BY, AZ plus BZ. And this is, I could replace this with numbers. And so it would be very easy to understand what's going on. Now, you can also go about it in another way. So here I'm just dealing with the coordinates of the head points. I could go about it by draw the operation. So here I have A and here I have vector B. To add B to A, I just draw a copy of B in the context of A. To be in the context means that the tail point is not at the origin anymore, but the tail point is at the head point of some other vector other than the origin. So of course, here I say that when I draw this in this gray color, it's in a way to hint that this is in the context of A. Actually, we don't have vectors with the tail not at the origin, but it's a helper. So we can see, okay, if I would place a copy of B on the head point of A, the end position that I get is the same result that I get here in the algebraic solution. So the coordinates that I would get for this position, let's say S for some, would be the same as this. So this is a very fundamental thing. I can of course add 4 vectors, and so here I have them all added together. And you could ask, well, what if I, instead of adding this one first, I first add this one? Well, that doesn't matter because this is a commutative operation, just like it was in scalars. So A plus B or B plus A is still equal to the same value, to the same sum value. So here I have the position A, and I add the vector OB, this vector here. So I draw it in the context of A. And so, of course, I get to this point. If I start with B and I add OA, I'm going to get into the same position. So it doesn't matter which order you add things, for example, in this node. Let's check the world position. So here I talked about context. And so, of course, there's some instances of that here in Lightwave. So we have, for example, let's say I have here the world space that I've talked before, the scene space. And let's say I have a cube item that I move around. And so by moving it away from the origin, in a way, it's like I'm defining a different space. In here, I'm going to disregard, other transformations other than position transformations or translation. So I'm not going to account in this context here. These concepts are not to be understood. Like I could rotate, scale an object, and it would still be what it is here. This is just 4 positions. Imagine just move something around. You're not actually rotating it or scaling it. Just moving around away from the origin. And so we have that this cube, I can access this local position, meaning the position in the context of the item, of the object. So the vertices positions is accessible, for example, here in the spot info node or the point info node by default. And so I have here the object spot or the object position. And so it will be this local position here that is relative to the item, to the space that the item defined. Now we also have another position, which is the world spot or the world position, which is relative or referent to the world space, not the item where it's inserted. So these points, this mesh belongs to this item, but these positions, the world positions, are referent to the world space origin. So if you look at here, basically to find the world position, I just add the local position of the vertex to the position of the item. So the item position plus the local or the object spot is going to be equal to the world position of that vertex. Same for example, here I'm talking about in a way of hierarchy. So here I have the object and the vertices of the object, and here I have the parent and the child item. So here I have the parent and I have the local position. So these positions that we animate here, that we get to go to the graph editor and animate them, they are positions that are relative to the parent. And so this local position here, it's not the same as the world position. So to get to the world position of a child item, what I have to do is, in a way, I could add, if I'm just changing positions, I could add the parent position relative to the world to the child local position referent to the parent. So this plus this equals to the world position. So this is just a small example of this simple diagram here. Some positions are not relative to the world space, but they are relative to local context, and that's why I call them local position. Anyway, let's look into some applications of this. Here I have this position, and let's say that I want to constrain it to a point in this mesh. I'm going here to the nodal motion, and I have this point info node by dpkit, and here I have the add scale mesh, which is this mesh here. And if I connect, if I put here this in the position, let's say there's a vertex that is at this position within this object, but I'm not actually constraining this position, this item, into the world position of that mesh. To do that, I could add that local position, just like I've seen here. So this local position, I could add it to the position of the item. So if I come here, and here I have the add scaled mesh, and I could add that position and add it here. And now it's going to be constrained to the world position of that vertex. Of course, if I put some rotation or scaling, that's not going to be the same, but I'm not accounting for those transformations at the moment, just the adding of positions in a certain context. Let's look into another example. So here I have an item that it's a parent and it has a child item. So when I move the parent, the child follows, and when I move the child, the parent is unchanged. So I could, let's say here, have the position of the child, and I could put the point, the position of the child here, fitting here, and so I get this position here. So when I move the child relative to the parent, this is what I get. Now, what if I want to constrain this position to the world position of the child? Well, I can of course add the position of the parent. So I could add this and come here, I have the parent item, and then just add these two together, just like I had here. So the parent position plus the local position of the child, and now these are constrained. So when I stick to just moving this around, you can see that those match. Now you don't need to actually go through this and add these things together. I can just use, in this case, these nodes have the appropriate ports. So for the child item, I can just add the world position, and so this will work, and it will do just the same. And here I can add the world position for the vertex, and so I can add this in here. And now when I move this box around, it's actually gonna constrain to that position regardless of where I move it. So this is a simple way to understand these. Of course, when I rotate things with these, they still work. So when I rotate this box, it's still constrained and still on that position. Same for this one. When I rotate the parent, etc., it's still constrained. The addition was just to show and give a bit more insight about this dynamic here of local item spaces and world space and adding those together. Now let's look into something else. Let's look into an operation that sort of combines the add and the scale, and so it's a node called addScale. So what addScale does, it adds two vectors, but there's the second one is scaled. So here I had, just like I had before, so here I had a plus b, and so here I had also a plus b. But in this case, what happens is that b is scaled. I just don't add b completely, add, scaled versions of it. So if the scale is 1, I'm going to get the sum. So the sum is a plus b. If the scale is 0, I'm just going to have a. So it's just a because OB was scaled into 0 length, so there's nothing to add. And then there's all these in-between values, or I can even go beyond that. And so basically there's a line that is defined by that. So I basically slide a position along that line in which the vector OB is like the unit. So we can see here the algebraic, here we've seen the geometric representation. Here's the algebraic representation where to each coordinate of A, we add the coordinates of B, but multiplied by the scalar. This is something that we can see, for example, very commonly with, let's say, morphs. So here I have this add scaled mesh object, and let's go here to the form tab, and we have the morph mixer, and here I have a morph already ready for it. So you can see that this is what I'm doing. I'm adding a position, but I'm scaling it. So it's not just I click and I have a morph. I control how much of it I do have. So this is an add scale operation. I'm adding position to this mesh, especially if it's a relative morph. And so I'm here controlling how much of it is. So I'm going to put this to 0. I'm going into the displacement node editor. And so let's talk a little bit about displacement node editor. So displacement node editor is basically an add operation. Whatever I put in here is going to be added into the current positions of the mesh. So let's say I have a vector 0, 0, 1. When I plug this in here, I'm not replacing the positions they currently have by 0, 0, 1. What I'm doing is I'm adding 0, 0, 1 to all the positions. So that's why when I plug that in there, it sort of seems like the whole thing just moves 1 unit on the z-axis. And of course I can scale this, and I can place this in here, and this allows me to control how much of it do I want that movement to be. So here I'm scaling this 0, 0, 1 vector, and so I can have more of it, or I can have less of it, or I can even flip the direction in which it's moving geometry by multiplying by a negative value. So I can also have, since it's the node editor, I can also have other things driving this control parameter. I could have, for example, this texture, this UV texture, and if I plug it in here, you can see that now this is pushing the points in that z-axis direction, but not all points are pushed equally. Depending on the image, some points are pushed more and others less, and so it means that a face comes out of this. I can also use, let's say, that I'm not very happy the fact that the back of this is being pushed as well. So let me go here to modeler and come here to add scale mesh, and you can see that there's a weight map in here. It's called WDisplace. So basically it's just painted on the front of the front vertices. So this means that when I plug this WDisplace weight map here on the opacity, I'm going to prevent these from being pushed. And so this in itself is also it's also scaling the information that is coming out of this. So this is a scalar value that is being multiplied here on the color. Of course, this is a grayscale, so it doesn't matter much, but it acts just like scaling the vector. And in the end, of course, we have the add operation being performed by the output. So scaled plus add, so we have an add scaled operation. Of course, like something like morphs, like I've shown previously. And so here I have this morph, this relative morph called mface. And so basically this is the scaled part, and the add part is in the output, so add scaled. And so when I move this like this, I can just put the relative morph to 0, or I can go really crazy about it, or even go into negative, etc. And again, since this is the node editor, it means that I can, for example, to have things driving the amount of this morph. I can, for example, have this spot info node that will give me the point positions relative to the object space, to this mesh space. And I can check the y-axis, for example, and say that, okay, if the y-axis value is greater than 0, I want the morph map to be, to be at its full force. Otherwise, I want to kill it. So let's say if I plug this here, now the points that are above 0 on the y-axis do get the morph applied, and ones that are above get nothing. And of course, I can, let's say, change this parameter and sort of animate a transition here, a really abrupt transition, I might say. But there's definitely there's a big open door to control these maps in such way, so that everything is very easy to drive other things with other information. So something that is you'll probably have more fun with here in the node editor that you will have in the morph mixer. Let's look into another aspect of the add scaled to define coordinate spaces. So let's come here and I have this position vector. And so one way to also look or decompose this vector is to check its component vector. So here I have basically the x, the y, and the z are vectors that are added together. So if this point here has the coordinates 2, 3, 4, basically the standard basis unit vectors, these ones here that define the 3D space that we are on, they were scaled by the scalar amount corresponding to the coordinates. So here I have I hat times 2, j hat times 3, and k hat scaled by 4. And these added together, so we have x, y, and z, they arrive to that defined position. So of course, since this is a fixed reference here, the standard basis unit vectors, these are not going to change much, but we can see here interactively as we change the position that those scaled versions of our bases, they arrive to that position by being added together. And of course, when we go into matrices and we start to change these axes, it's still something that applies. So even though the axes might go crazy, we can still see them arriving at that position, as we can see. But at the moment, of course, again, in this case, this is a fixed reference. I'm just showing that these are used to build positions up and as they define spaces. So another thing to show about add scale here is that, of course, add scale is not as commutative as the add operation. So here I have that this is commutative. It doesn't matter if you do a plus b or b plus a. Now with add scale, of course, it kind of matters what you put first, because of course if you do a plus b times, let's say, 2, it's not going to be the same as b plus a times 2, unless of course they're both equal, unless of course a is equal to b, so in that case it's going to be the same. But otherwise it's going to have different, going to arrive at different positions. Of course, if s is equal to 1, yeah, then it's also going to be the same. It's going to be just like this, right? So let's look into that here. I have a quick demo. So I put this to one value on the x-axis, and this other vector shows up, vector r. And so as I move this on the z-axis, you can see that I'm scaling so here I'm scaling the vector, the position p, and so you can see that it's being scaled and added onto the context of r. So I can see the result of that add scaled operation. And here I have the other way around. I have so in one place I have p plus r scaled, and in the other I have r plus p scale. And so you can see that of course they have different outcomes depending on the scale that here is controlled by the z-axis. Of course, if this scale, I'm going to put 1 here on the z-axis in the control object. Of course, when the scale is 1, yeah, they're going to be in the same position. It's going to be the same as just a simple addition. But whenever this is changed, of course, they're going to be in different positions. And of course, if I go into negative, let's say -1, this now becomes a subtraction, because to p I'm adding a flipped version of r, and to r I'm adding a flipped version of p. And you can see that the result of them is similar. It's just that they are the flip of each other. So this vector is equal to this vector, but they're just flipped. So we're going to talk about subtraction next and position deltas.